And there are, of course, discussions how to mitigate that effect. That means how to change it. How can we sort of possibly get the CO2, separate this out so that it doesn't go into the atmosphere? And this is in, there's a lot of research being done, and it's called CCS, Carbon Capture and Storage. And it's still not clear to which extent you can really do this and what the prices you have to pay. But what we want to discuss here is actually rather talk about the options we have to reduce the CO2 emission. Not carry on the way we have done it before, but rather look at the possibilities to produce electricity and also heat without having CO2 emissions. And this is like a listing, actually, which I think is fairly important to be aware. It's not only one solution you have. There are several solutions, and you have to do everything together. And especially you have to develop these techniques. They are not all developed yet. So it's important for you guys, actually, you learn this, how to deal with this, and then develop techniques later to make this more efficient and put this into place so that everything then works and we can avoid actually the CO2 emissions. And let's quickly go through this. Should we have a break, actually? 5-minute break, or we just carry on? We have one break, actually, that's later. We don't observe the bell. Okay, good, let's go on. So in the moment you increase the efficiency of the conversion process, then of course you reduce the CO2 emission. You can reduce the losses also during transport of energy, a very important aspect. Use energy saving measures. So don't put on the heat and at the same time put on the open the window, right? This is not really energy saving. That's wasting energy. That increases eventually CO2 emission. Go to fuels that are less CO2 producing. Example, when you use a power plant that's based on coal and you compare that with a power plant based on natural gas, for each kilowatt hour you save about 1/2 of CO2 when you use natural gas. So going to a different kind of energy source can help you actually in reducing the CO2. And then of course what we had touched upon already, use renewable energy sources. And the more you use renewable energy sources, the better it is. But look at the overall picture, because you also need energy to build a wind turbine, to build a fuel cell power plant, to build a solar energy. You have to take into account everything that essentially produces CO2 in the end. But the prospects are definitely much higher that you save CO2 here. Use electromobility instead of your internal combustion engine. But see that the electricity you use in your electric car is produced from renewable sources and not from coal power plants. And then one possibility is what I mentioned before, is use CCS in order to get the CO2 actually not being admitted into the atmosphere, and then possibly even use CO2 to make something else out of it. So there are a number of options, and all these options are really important. Now, what are sort of the two possibilities, the principal two possibilities to produce electricity? When you have chemical energy and you want to have a sort of electricity, there's one way, that's the conventional way of going through a heat process. So you have a combustion, and that combustion produces mechanical energy, and then you do sort of get electricity. But you can actually also convert chemical energy into electricity by using a fuel cell. The fuel cell is a direct converter of chemical energy into electricity, and what it does, it makes this process going from here to here actually more efficient. You see, it's a direct process, and the other one is an indirect process. And this is actually illustrated even more clearly in this graph, where you see actually all the intermediate steps. When you have a fossil fuel, they typically go actually through a reforming process and make some other chemical energy from this, and then these are the different ways to produce electricity with a turbo machine or a piston engine in the end to have electricity. But you can actually use also fossil fuels like natural gas and make hydrogen from it and then put it in a fuel cell. And you see that this has advantage already because it's less cumbersome than this, and it's more efficient than this and gives you less CO2 emissions. Now, having mentioned the fuel cell, then the question is, how does the fuel cell work? Now, if you have learned something about electrochemistry already by the previous lectures of Professor Chen, then this one is probably very simple for you to understand. You take an electrochemical cell, that means you have electrodes, you have an electrolyte, you have actually a membrane that separates these two compartments, and on the electrode here, let's say a platinum electrode, you put some hydrogen, and on the other electrode you put some oxygen. Now you can take the oxygen from air, so you just take air here, but that's available. And then when you look at these little pictures here on the left and the right side, then you see what the processes, the electrochemical processes are. Hydrogen comes in here and goes to the surface, and the hydrogen becomes oxidized to protons. And each proton has a positive charge. That means you take an electron away, and from one molecule of hydrogen you take away 2 electrons. And when you look actually at the other electrode, you have oxygen come in. This is the oxygen comes in, and you take 2 electrons and put it actually on the oxygen and plus 2 protons, and then you make actually a water molecule. So this is an oxidation reaction. This is a reduction reaction. And so because this is reduction, you call this cathode, and because that's an oxidation reaction, you call this anode. And this way you see how directly you can make out of these few reactions, the oxidation of hydrogen, the reduction of oxygen, you can directly make electricity from it. So you can actually, with that process, with the electrons coming from here, you can funnel them through a external load and then go back, and this is how you close the electric circuit with electronic charge carriers in the external circuit and ionic charge carriers in your cell. So this way, essentially, you can make by electrochemical means electricity from a fuel, and that is much more efficient than using a combustion process and driving a generator. And now the real fuel cell doesn't look like what I've shown you. That would be much too cumbersome. So one actually looks then at the elements of the fuel cell in like a flat cell design. And you see this here. This is the electrolyte layer, and this electrolyte layer can be a polymer, can be a ceramic material, can be also liquid material. It has to be ionically conductive, And it should not be electronically conductive, because otherwise, because of the voltage difference here, you would have an electronic short circuit current. And then this would be the cathode, where you have the oxygen come in, and this is the hydrogen on the anode side, and you have a connection through an external load, and then you sort of close the electric circuit. Now, so what we are going to do now is that we sort of look at these materials in greater detail, their properties, how the mechanism works, and so we are going to start actually with the electrolyte material, with a membrane, and look actually at the possibilities and try to understand this for initially the situation of so-called low temperature fuel cells. Now, let's look actually again very carefully at the criteria for such a membrane. And you see it's a long list. And because it's a long list, it shows it's a complicated problem. So let's go through some of these aspects and then later discuss them in detail. What you need to do is, in the membrane, you transport the protons that are generated on the anode. You need to transport it to the cathode, because you need to close the electric circuit. They have to be chemically stable for several thousand hours. Typical operation time, when you have a stationary fuel cell that want to last for some time, 10,000 hours is like what it has to sustain. It's also a separator, because on the one side you have hydrogen, on the other side you have oxygen. So they shouldn't mix. They have to stay separate from each other. So the membrane has to have essentially a zero permeability for the gases. A very important aspect. And that separation has to sort of take place and be active under various conditions. That means normal operation conditions for startup and shutdown, and when you have fluctuations actually in the load on the fuel cell. So when there is actually a larger load, that means the fuel cell have to produce more electricity or less electricity when it has less load, and you have a stream of hydrogen and oxygen coming to the electrodes and being sort of in the electrode distributor. It should not go actually through the membrane. Then it has to be mechanically stable. You need to have a sufficient tensile strength. It has to be dimensionally stable during swelling. So why is swelling actually an aspect then for a membrane? Can anybody say actually very quickly offhand why swelling of the membrane is an issue? Just think about the reaction. What's the reaction product when you run hydrogen and oxygen on the both sides of the fuel cell? We have shown this here actually before. Oops. You remember this reaction? Oxygen comes in, and then you have two protons, and then you form water. So the electrochemical reaction forms water. So there's a continuous production of water. Where does the water go? Well, it also goes to the membrane, and then the membrane swells. So that has to be sort of within the dimensions of your fuel cell. So that's very important actually to, oops, I'm going in the wrong direction. Sorry. Okay. So swelling is really an issue actually for some of the materials. And then of course, receptive to cracking and creeping, that does mean the mechanical stability must be maintained. You must have a high gas permeability for an adhering film on the electrode, because the gases have to come to the electrode, but should not go actually through the membrane. low gas permeability of the membrane. Water management, I just addressed this. Water uptake and transport during operation is important. And then in the end, it has also to be inexpensive. A lot of problems, right? Okay, but people have worked on it, and let's look at some of the aspects. So when you look actually at the question of why is a membrane conductive, we have to understand, because we want to have a membrane that has a very small resistance in the electric circuit. And that means it has to have a high conductivity. So we have to actually understand what conductivity is, and we look first actually at the question of the proton conduction in water. So you know actually how you defined a conductivity. So you apply actually in a standard cell that has a certain distance, certain cross-section, apply a voltage, and then you measure a current, and that current is given by the resistance. And you can place that resistance then by this element here, which is like d, the thickness, divided by the area over which that takes place. And that's the specific resistance of the material. And that can be then transformed into a conductivity that's shown here. So this is actually the decisive materials property of any kind of material. You can use in 1 molar sodium chloride solution that has a certain resistivity or conductivity actually. You can have hydrochloric acid actually. Now when you compare these two, then there's one interesting fact. The conductivity here is much higher than is here. And do you know what the reason is? If you compare sodium chloride with hydrochloric acid, why is the conductivity of hydrochloric acid so much larger than the conductivity of sodium chloride solution? Concentration is the same as 1 molar, both cases. Any suggestion? Essentially, well, that is more than the explanation, more than the question even, yes, because essentially the proton has a much higher mobility than the sodium ion, and that gives a higher conductivity. And why is that? That's actually what you answered, because of the special mechanism actually of conduction, and we will actually talk about this in a moment. Very good. So we need actually a high proton conductivity, and so typically you have solvated ions. So the proton is not a single proton like floating around, but it actually associates itself with a water molecule and forms a so-called oxonium ion. And this is a very important aspect for the so-called hydrogen bonding in aqueous solutions. And you will see actually in a moment how important that really is for the membranes, how the conduction process for the membranes is. And this is exactly what was said in the moment before. There is this hopping mechanism, but actually it's not only a hopping, it's maybe a bit more complicated. When you have actually an oxonium ion here, like an H3O+, and then you have some water here, what happens is that the bond structure changes from this one to this one. So, and then you change actually the charge as well, and this is then like the jumping actually within the water structure, and that, since it's not a physical motion of one proton that goes from here to here, but this flipping of the hydrogen sort of atoms, That makes the fast transport. And actually you can say take this picture, and you can, by flipping this around, you can very quickly get the positive charge here on this side. And this is very important to understand that this makes for the high conductivity. This is actually a little more sophisticated way of describing this. Is this play actually between the breaking of hydrogen bonds and the formation of hydrogen bonds, and you form actually these sort of association. It's an association of a proton together with a water molecule, and it's not only one water molecule, but these are more actually than one water molecules. Okay, so what we can say actually about this mechanism, a number of things, but it all actually boils down to, I will not go to all this in detail, but we have to understand that the conduction, the ionic conduction in a water system, especially when you have protons in there, is a sort of a special process that has a very low activation energy. It's typically 25 millielectron volts. That's the energy necessary to break and form a hydrogen bond. And whenever you have actually a proton moving through the water structure, you need to break the hydrogen bonds. And so this is the number that goes into it. You can actually transform such a mechanism into a solid material, as long as the solid material has enough water. And we will see actually in a moment, when we go to sort of different membrane materials, how that actually plays an important role in the conduction process. Now, this is just a confirmation of this again. It shows the diffusion coefficient as a function of concentration, and the diffusion coefficient sort of goes down actually with increasing concentration. And what you see here is the difference between, this is actually showing the sort of diffusion coefficient based on conductivity, and that's the diffusion coefficient of water molecules themselves. This is sort of for the protons, and this is for water molecules themselves. And so this is what you call actually a self-diffusion coefficient, which is one that is very large for water. Water is a very, very special material, and it's different from, in that sense, from all other materials, that even in liquid state it has a structure that means that you have an agglomeration and aggregation of a lot of water molecules, but these are not static, but highly dynamic because of the high self-diffusion coefficient. So that means it constantly forms aggregates, and they disintegrate and they form newly, and that is something that is very specific for water. Now, the membrane material that's mostly used in low temperature fuel cells is naphthalene. And naphthalene is a material that's shown here. It's based actually on PTFE. Does anybody know what PTFE is? Everybody of you has been in contact with PTFE. I promise you. Maybe you're not aware of it, but you have been. Does anybody know PTFE? Various situations. What's your hobby? What's your hobby? Cooking. I assume cooking is your hobby, right? It's true, right? I knew. Okay, then you have a pan, right? and you put the pan actually on your stove.
Some oil when you cooking, add some oil and your food is cooking. If the PTF is the level on your pan, it will not be black.
Okay, and the point is that you need only very little oil actually in the pan, because the PTFE prevents actually from the food to stick on the surface of the pan. So you put the PTFE on the surface, right? And then you need only very little oil. If you have no PTFE, you need a lot of oil so that the food doesn't stick to the pan, right? So that's one possibility where you need PTFE. There are others actually that you use this for impregnation of clothes actually, so that there is no water actually comes through, so it becomes waterproof. And there are a lot of applications actually of it. You use it as a grease when you have actually your door makes a creaking noise from the hinges, right? Then you apply some spray, which is not oil but PTFE, and then it doesn't creak anymore. So that's the basis actually. PTFE is the basis, the chemical basis of the Nafion membrane. You see, this is sort of the formula. You have the CC bonding, there's a chain here, and then you have these fluorine groups in the side. Now the Nafion has some modification to it, has these chains, but then it has side chains, and these side chains are partially oxygenated. You see that here. And then in the end of each side chain, you have a sulfonic acid group. You see this, SO3. And the sulfonic acid group, it comes actually introduced by treating this with sulfuric acid. And so then you establish this group. And the SO3 is able to dissociate a proton so that you get SO3 minus, and you have actually one proton that can dissociate. And when you bring this in contact with water, then the proton can go into the water and form a acidic water phase. Okay, this material was discovered in the late 60s by Groth. He was actually a Dutch scientist working for DuPont in the United States, and he found that this has an excellent thermal and mechanical stability because of these properties here. We just discussed that. And it can be used for a number of purposes. In fuel cells, chloralkali production, it's being used, water electrolysis, and so on and so on. However, the price is rather on the high side. So when you look at the fuel cell and you look at the different sort of contributions to the cost of the fuel cell, then the membrane plays an important role. Now, let's look at some of the properties of this Nafion. And you see, actually, there are sort of two aspects in looking at this polymer structure. There's a hydrophobic backbone. This comes actually from this PTFE, which is actually also called Teflon. Some people call this Teflon. And the sulfonic acid groups that are hydrophilic. So as a consequence, water would go actually only to the situation where the sulfonic acid groups are. So this is in this, let's say, cartoon. You see here the polymer chains. They are shown here, and then you see here the sulfonic acid groups in these side chains, and you see that here you can accumulate water on these side chains. And the proton conductor of the Nafion is only active when you provide water. Without water, there is no proton conduction. because the protons need to move in the water in order to produce, to transport electricity. You can actually say what the equivalent mass is and an ion exchange capacity that's related to the equivalent mass. So there are a number of characteristic parameters. But one thing is really important to remember is the conductivity of the membrane is crucially dependent on the water content of that membrane. So you have to be careful when running a fuel cell that the water management is maintained, because when you deprive the membrane of water, then suddenly the resistance goes up and conductivity goes down, and then the fuel cell becomes less efficient. Okay, so when I look then at the structural properties of the naphthalene, I can distinguish like three regions. There's an aqueous phase, there's of course the interface that's created by the sulfonic acid groups then to the water, and there's a hydrophobic phase. That's the backbone of the polymer. Now with increasing water, I mean, you have seen this cartoon. When I put more and more water in there, what does the membrane do? It starts swelling. And that's definitely a property of the naphthalene membrane which I have to take into account. Then there is sort of, depending on the number of sulfonic acid groups, you can say what the distance between these sulfonic acid groups is. It's about 8 angstroms. So that means actually there are a lot of sulfonic acid groups on the surface of the polymer. And you need about 2 to 3 water molecules to get a dissociation of this proton from the sulfonic acid groups. And then you need actually a total of 6 water molecules for separating the proton from the sulfonic acid groups. I mean, you have to actually shield the positive charge of the proton versus the negative charge of the SOFC, and you do this by having complete solvation of the proton. So that's very important, and it shows actually how much water you really need. You need 6 molecules of water to get all the protons solvated. And that's a lot of water. Okay. Then there's a reduced polarity of the water that has to do with the confined space. And that, I mean, the confined space means how wide these channels are in the naphthalene. And when you have water molecules that sit close to the channel walls, then they also have reduced mobility. So that changes their dielectric properties. So one can actually do some simulations then of the properties of these membranes. This shows actually some of the correlation between, let's say, the vapor pressure is shown here and the number of moles in the material. And then when you go actually to higher ratios, then you come even in the so-called two-phase regime, where you have really the polymer and liquid water being present. Now, we have looked at the sort of mobility of protons and the diffusion coefficients of protons and water in water itself or in an acid. But it's important to see that actually also in the naphthalene membrane, and this shows actually how this diffusion coefficient is a function of the ratio between water and sulfonic acid groups. And you see here the number, we said 6 is the minimum you need for getting the proton shielded from the sulfonic acid group. But you see that even for numbers like 50 or even 100, you still have an increase in diffusion coefficient. So that means for the conduction process that there is no saturation in that effect, but even large amounts of water are beneficial for the conduction. But of course, in the operation, they are not beneficial. So there is actually like a catch-22. It's good to have a lot of water for the conductivity, but for the mechanical properties and the functioning of the fuel cell, there's some limitation. And you see that the conductivity as a consequence, this is the diffusion coefficient, and this is the conductivity plotted here on the abscissa as a function of temperature, and you see that this value really goes up the more water you put actually into the membrane. That's actually for a given membrane material, the so-called 1100. Okay, now when you transport protons in the membrane, then, as I explained before, you just not only transport the protons, but since the protons are solvated, they're surrounded by water, you transport also the water through the membrane. And that's actually a very important aspect you have to consider, because in the membrane you have the transport of protons to close the circuit of your fuel cell, and at the same time what you do is you transport water essentially from the anode to the cathode. So since the fuel cell works actually on gases, hydrogen and air, you arrive actually with a lot of water on the cathode side, and that's something that is part of the management but you have to take into account. And let's look at some of the structural situations of the membrane, structural models. There have been actually a lot of attempts to describe this, and this is just sort of some of the models that have been actually done, and there are different models also. One model that's shown here is that you have sort of inverted micelles. You see this is about 4 nanometers and the distance of these inverted micelles of about 5 nanometers. Now when you increase the water content of the membrane, then essentially these inverted micelles grow, they become bigger, so the diameter increases. But looking actually at these two in the proximity, when you increase the size here and increase the size here, what happens? They become actually closer together, and essentially what they do in the end, they actually merge and become one big micelle. So the structural properties change also with the water content. And that is definitely something one needs to take into account. And one thing similar, but more in a statistic way, is shown here, and that is to look at the membrane for different water contents. This is sort of a low content, this is less than 2, 14, 22. This is like the stoichiometric numbers of the ratio of water molecules to protons. And you see that this is sort of isolated water when you have less than 2. When you have 14s, they are all connected with each other. And by even larger ones, you can have preferential pathways because you get a lot of larger channels, like I've described here, when sort of 2 micelles actually merge. And that's sort of a different presentation also. I don't want to go into detail here. Just want to see that we finish this part. Okay, this is just an illustration actually of sort of similar thing I just said. This is the dry membrane, this is a somewhat swollen membrane, and when they become sort of enough water, then they become really interconnected. You see this here, and sort of individual micelles start to merge and to form sort of big ones. And here you have percolation pathways in the membrane for the water that gives you then conductivity. Okay, that's sort of what we wanted to discuss about the naphtha membrane. And now we would come actually to catalysts and electrodes. I would suggest that we now have a break. I would say 5-minute break. Is that okay? To recover and then go into the second phase. Okay, thank you very much.